Hello everyone, my name is Trey and I'm from grade 12 Advisory L. And today I will be showing you the simple harmonic motion equation and as the derived formats of it. Before we get into that, I'd like you to visualize a disk that is simply rotating, and atop that disk is a coin. This coin is also rotating alongside the disk. Now we can isolate the movement in the x-axis of the coin, in which would make the simple harmonic motion of the coin, as well as an oscillation movement or a pendulum motion, as what you want to call it. We can also rotate this motion by 90 degrees as though it was a cosine or sine graph that was moving. By that, we can use an example of a cosine graph in which we have the x-axis again, rotated 90 degrees. And we have three main points of the graph: the equilibrium, the resting point of the graph, at which x is equal to 0. Two other main points, the minimum and the maximum, that has the x equal to a, or amplitude, of the graph. Following this graph, we are now using the first equation of the simple harmonic motion, which is as follows. X in reference to time is equal to amplitude times cos angular velocity t. This, amongst many other equations of the simple harmonic motion, equates to the displacement. We can also turn and derive this equation, in which we can equate it to the velocity as well as the acceleration of the graph. Now, we can infer that the first derivative of the x equation will lead to v, velocity, as well as similarly, v derived would also equate to acceleration. Deriving this equation would mean that it is dx, or d displacement, over d time. This would equal to negative angular velocity times a, amplitude, times sin, angular velocity time. This again is the equation for the velocity, at which we can also later on turn into the acceleration. The acceleration, much as stated before, is the same as the second derivative of x, in which is equal to the velocity, dv, over d time, in which equates to negative angular velocity times positive angular velocity times a, amplitude, times cos, that's a little too far right, times cos angular velocity time. This can be simplified a little bit to negative angular velocity squared times amplitude times cos, well, the same as before. Notice that the right hand side of the equation is exactly the same as the x equation beforehand. So we can simplify that again into negative angular velocity squared times x. Going back to the cosine graph, the usage of the equations vary among the users and person using it. The first equation, dx, can determine the level in which the graph resides. The second equation, the velocity, can determine how fast the graph moves, as well as the third equation, which can determine the acceleration, if there are any. That is it for my brief explanation of simple harmonic motion equations and its derivatives. I hope you liked the video, and thank you for watching.